Your theory that each universe could be born from a black hole is a compelling and imaginative way to think about the nature of reality. This idea, while speculative, overlaps with several advanced concepts in physics and cosmology. By cross-referencing everything we know about matter, the elements of the universe, and our current understanding of cosmology, I can highlight points where your theory resonates with or diverges from established scientific ideas. Here's an in-depth exploration. Matter and the elements of the universe. The universe is primarily composed of matter or baryonic matter, dark matter and dark energy. Baryonic matter makes up stars, planets and living beings. Dark matter interacts through gravity but not electromagnetically, and dark energy is a mysterious force driving the universe's accelerated expansion. In our universe, elements form through processes like nucleosynthesis during the Big Bang, which produced hydrogen and helium, stellar fusion and supernovae, which created heavier elements. If universes are born from black holes, each new universe might inherit or reset fundamental conditions, leading to potentially different compositions or periodic tables based on different initial conditions. At the heart of a black hole is a singularity, a point where densities become infinite. The laws of physics as we know them break down here, suggesting that matter could undergo a state transformation beyond our comprehension, possibly recycled into the creation of a new universe. Cosmology and black hole universe theories. The idea that black holes could spawn new universes is linked to theories like the baby universe hypothesis. In this framework, black holes are not just destructive objects, but could be bridges to new universes, each with its own physical laws and constants. This resonates with the idea of a multiverse, where universes with varying properties emerge from black holes in parent universes. A white hole is the theoretical time reversal of a black hole. It expels matter and energy rather than absorbing it. While white holes have not been observed, some theories propose they could be connected to black holes, possibly representing the Big Bang of a new universe. Stephen Hawking's work on black holes showed that they emit radiation known as Hawking radiation and can eventually evaporate. The information paradox, whether information that falls into a black hole is lost, suggests deep mysteries about the flow of information and matter. If information is not lost but transformed, it could imply a conservation of some form across black hole boundaries, supporting the idea of connected universes. Quantum gravity and the nature of singularities. Quantum gravity theories. General relativity describes gravity at large scales, while quantum mechanics describes the other fundamental forces at microscopic scales. However, these theories clash at singularities like those in black holes or the Big Bang. Theoretical frameworks like loop quantum gravity suggest a bounce at singularities, potentially transitioning a collapsing universe into an expanding new one. The holographic principle, suggested by Gerard Hooft and Leonard Susskind, proposes that all the information in a volume of space can be represented on its boundary. This idea hints that the three-dimensional universe could emerge from a two-dimensional surface, much like the event horizon of a black hole. This perspective aligns with the notion that a black hole could encode the birth conditions of a new universe. Entropy, thermodynamics, and the arrow of time. Entropy and the second law of thermodynamics. Black holes have entropy proportional to their surface area, and the universe too increases in entropy over time. If each universe emerges from a black hole, this might reflect an ongoing process of entropy reset or transformation across cosmic cycles. The arrow of time. In each universe, time seems to move forward due to the increase of entropy. If black holes give birth to new universes, this could suggest a cyclical or branching multiverse, where each baby universe starts with low entropy, setting a new arrow of time. Multiverse implications and cosmic evolution. Eternal inflation. The concept of eternal inflation proposes that inflation, or rapid expansion, never completely stops, and that pockets of space continue to spawn new universes, akin to bubbles in a foam. Each black hole could act like one of these pockets, connecting inflation to black hole formation. Fine-tuning of constants. Different universes born from black holes might have different physical constants, such as the speed of light, gravitational constant, or particle masses. This could explain the fine-tuning observed in our universe without invoking a designer. Different universes would naturally vary, and only those with the right conditions for life would see observers like us. Summary and big questions. Your theory finds intriguing support in several speculative but mathematically sound areas of physics. However, some big questions remain. Initial cause. If universes are born from black holes, what caused the first black hole or universe? Does this process have an origin, or is it truly eternal and self-sustaining? Testability. How can we empirically test or observe connections between black holes and new universes? Would there be detectable signals in our universe hinting at such a process? This cross-referencing shows that while the black hole universe theory aligns with some theoretical frameworks, it remains at the frontier of our understanding, bridging known science and the speculative edges of cosmology.